you say that again?
So you must have University of Hawaii.
Yes, sir.
Yes. Well, hi, my name is Bob Wood. I'm one of the judges that's involved with looking at your final report and your the materials that you've submitted for the competition. So we have about 14 minutes. I mean, we have to be pretty strict on schedule because we have a number of teams to go through, and then we're reusing this channel basically for a whole nother set of teams afterwards. So I wanted to take an opportunity to ask you a few questions about your rocket to help me understand some of your design rationale more than anything else, okay? And if there's anything that I have asked that's not clear or anything, please just kind of let me know and I'll try to repeat the question, okay? One question is kind of, I've been to Hawaii a number of times. I'm wondering, when you look at recovery design, what are you doing that's maybe special to be able to handle hard landings on lava, you know, presuming that you're actually launching in Hawaii? Do you have any thoughts there that you can share?
Well, first, can you hear me all right, sir?
Yes, I can, Jerry.
Okay, awesome. Thank you very much. So we are not launching the rocket specifically at Hawaii because of regulations limiting the size and caliber of which rockets can be tested and flown here. Our current rocket, of which we call Apophis, is planning to be flown at Exper/Arliss, and because of the size of rocket that it is, it's only to be flown on the continental United States because certain restrictions. So we have not really thought that far ahead of it landing on lava because we currently do not have the capability of testing if it possible that hypothetical scenario. Okay,
well, okay, that's something I was unaware of. I didn't realize you had the airspace restrictions probably there, right? Okay, perfect. One thing I noted in looking at your final report is kind of a bit of lack of detail about the rocket kind of engineering itself, right? There's a lot of things that you spent a lot of time on. You're talking about your payloads, but some of the little things like your motor mount design or rail buttons or other things along these lines, those kind of details are the kind of details that kind of level 3 TAPs would kind of pay attention to if they're going to certify a flight. I was wondering, you know, if you could elaborate a little bit on some of the manufacturing techniques that you used that would qualify this rocket as, you know, a good, flyable, safe level 3 rocket.
Yes, of course. So with regards to the motor mount itself, unfortunately, we actually finished the booster section about 2 years ago, so my memory is a little fuzzy on that. However, I do know some specifics. I cannot walk through step by step, but I do know that we use an aluminum fin can as well as a bolt plate to mount and basically create the space in which the motor will be held. And then there's also, if I recall, what's the name of it? What is it called? Oh, retention plate. There we go. There is a retention plate that allows that is attached to the bottom of the motor mount itself, which allows the motor to stay fixed inside of the booster section whenever the rocket is flying, of course.
I see. And so I guess there's an aluminum cap on that rear bulk plate. Is that correct? That you insert the rocket from the aft end of the rocket, or the motor from the aft end of the rocket, and then you screw that cap in place there?
Yes, sir.
Okay. So that's a little feedback for you. I think that would be helpful because there's many judges that actually don't have the same teams from year to year, or we don't have access to like previous flight designs, things along those lines, right? So on critical systems like thrust plates, motor retention, rail buttons, and things along those lines, you might not think they're critical unless a rail button breaks on launch, you know, that kind of thing. Those kinds of details are very useful just in the sense of completeness in any progress report or final report that you may wish to put in, okay? I wanted to ask also about your motor selection. and what kind of trade-offs that you went through to kind of select that particular motor for this rocket. It's not clear that you, I haven't seen like characterization data for this COTS motor, right? And I'm wondering what variables you may have been looking at in terms of either selecting that motor versus another COTS motor or selecting a different size motor. What was your rationale for selecting the motor that you did?
I believe my teammate Patrick will be more equipped to answer that question. So Patrick, if you please.
Yeah, thanks, Jared. So, Mr. Wood, to answer your question about why we chose our motor, so it's a pretty high-powered motor. It's like larger than a model rocket, and it was in a good cost range that we were looking for, and the reason why we chose a hybrid though, as it's I'm sure you're very well aware of, it's extremely safe, and that's exactly what we're looking for at the university. So even though like a solid system, we could get a lot more power, a lot more altitude. We don't really have any special storage facilities here at WCC. So that kind of, that's why we didn't choose a solid motor. And then a liquid system, the machinery is kind of complicated. So with the hybrid, then we could potentially test like throttling capabilities that like that's like one of the major benefits of a liquid system. So finding that middle ground with the hybrid where the components are really safe, and also still having the being able to learn from the realm of the solid grains. We thought it was a really good middle ground, and that's why we chose the hybrid.
I see. Yeah, and that makes perfect sense, right? What I'd like to suggest in your reports and presentations, and I did see in your video a lot of discussion about the hybrid motor, and your discussion about how that's a nice middle ground between pure liquid motors, which are actually quite dangerous, and pure solid motors, which if they're black powder, you have problems with storage. With ammonium perchlorate based motors, that's a little bit less so, except for humidity contamination, right? But being able to elaborate those details, kind of at a system level trade-off. If you think about what trade-off analysis, kind of at a rocket level, right? It's kind of trading off what the mission objectives are, with the physical characteristics of the rocket, and with fundamentally cost. So if you think like when NASA puts up a rocket, right? Those are the kind of main variables that they think through. It's very useful as you start describing a rocket and you're explaining why you've made certain design decisions to kind of think in that system trade-off space and say, you mentioned a couple things like cost, or you mentioned things like safety. These are all very valid reasons, but that means it makes it even more valid to put that into your project report. So people who are looking at the effort kind of understand kind of your thinking and why you made some of the decisions you did. So almost looking at it from a top-down design perspective. Why did you choose the airframe that you chose? Why do you, and again, it gets that right down to the parts. Why did you pick that particular fin plan, right? So these kinds of questions is just a good way to inform kind of your audience about what your design decisions are, right? So that they can understand your rationale, right? Does that make sense?
Certainly.
Regarding your payload, let's talk a little bit about what your general objectives around your payload were. Could you kind of give me a good synopsis of why you chose the payload project that you chose for this rocket?
As for the payload,
I think you're breaking up, Dale.
oh, sorry.
No, you're not coming through.
Can you hear me now?
Yes.
Okay. Sorry, I'll take something else. So for the payload, for what we were doing for the objectives, basically for recovery, we have the GPS, and then we have in the 2U both the telemega, and then since we're testing this new product called the X in a Box for the Hawaii Space Grant, it also had a GPS as for fail-safe, but also to test out new technologies. But other than that, for the recovery, we were also looking into IMU, inertial measurement unit, to take data while it is in flight, and then the camera for taking pictures when the 2U was ejected from the rocket, and it would descend and take pictures of the geography coming down, which is also, I didn't lose you, right? You're frozen on my screen.
No, you're still there.
Okay. Which for the camera, when it's coming down, it would take moving pictures and still pictures of the geography of the land below, which has various uses for just seeing a different land underneath, and then also getting data in a sense that way. So that was just things we're going over.
You're breaking. I think we might have lost you at the end there, Del. Perhaps a slightly different take on the question. So for the payload, are you primarily looking at basically validating kind of these types of technologies, such as various GPS and IMUs, and understanding what their capabilities are? Or is it to kind of close the loop, for example, on simulations using OpenRocket, or kind of at a high level, when you're doing an evaluation basically of these different types of systems? I use kind of the ST-IMU, same one of the DS1, I think, that you have in your design for doing guided rocket design, right? So is the intent in evaluating some of these technologies to kind of pursue kind of a long-term vision around engineering systems, or is it just to get more familiar with these kinds of COTS devices, or at a high level, what's the main purpose?
It's kind of a combination of both. We were going into this competition being relatively new to all of these electronic payloads, but we were also doing continued research from past CON-CC projects with the Kalea projects regarding the GPS, IMU, and camera. So it was getting a sense of learning about these new technologies, but also thinking of future ways and how they can be used to gather like data for location, and then also meeting the requirements for recovery and testing out the different technologies that we have, like the new one, like the X in the Box that we got from this the X in the Box people who were testing out the electronic payload for them and using it as a way to further our research on our designs that we had for the Kalea projects.
Right. Okay, well, that makes sense. And this is kind of falls into the same kind of feedback I'd like to give you regarding some of the other points, right? If you're thinking about like building a rocket, it's got a mission. It's almost like ConOps is like where all things kind of percolate from, right? People don't start with like saying, I'm gonna use a Delta Heavy, and then I'm gonna put a canister on top and put people in it. They basically start by saying, we're gonna go to Mars, right? And so when you start thinking about like the how do you describe the objectives of the rocket and how that percolates down through system design, it's really important to kind of be able to talk to why are you doing this particular payload, and even better, how is this an evolution or incremental engineering over what you've done in the past, so that it conveys that there is kind of a continuity of thought, and that there is a long-term strategic kind of view of what you're trying to do this year, right? And so that's just a little bit of feedback I thought I'd share with you. Does that make any sense?
Yeah.
I'm going to have to, we hit the bottom of our 15 minutes. I wanted to say thank you very much for taking time today and answering my questions. I've enjoyed reading all of your reports, and I'm looking forward to seeing you fly one of these days. Okay.
We are too, sir.
Thank you so much.
Thank you.
Thank you.
Yeah, thank you very much.